Yes, today would be a nice day to stay home. Okay, so everybody Coach Chromebooks real quick. We're going to go through today is the PowerPoint for Chapter 2. I'm going to go through this very quickly because we covered all of this pretty much last semester. And so they're introducing plate tectonics and earth structure, going back over a couple things. So I figured what we can do is today we can power through this presentation really quickly. Just kind of go over some of the big terms, recap what we covered last semester and what we learned last semester, and then tomorrow we can start on some of the assignments that they have for this chapter in the book. And the assignments are pretty good. There's going to be some interesting things to do, so I don't feel like we have to spend too much time on the PowerPoint. I do kind of want to go through it and show you the case study for this chapter, which is the San Andreas Fault, which we've all heard about, and just to kind of retouch on some of the things that we went through last semester. So let's get started on it. They have your, I already messed up. There you have your, what are they called? Your, I don't know, objectives. There you go. So sorry, Monday morning. They have your objectives that you're going to attempt to learn through this chapter, and it's not too bad. This is a pretty straightforward chapter. So what they start off with is the tale of two cities on a plate boundary, which is Los Angeles and San Francisco. They are both on opposite sides of the San Andreas Fault, and as that fault continues to move, Los Angeles and San Francisco are actually going to get closer together. The bigger earthquakes in the U.S. history have all been on the San Andreas Fault. So one of the really big ones was in 1906, caused a major earthquake, lots and lots of damage. I think we had another one maybe in 1980 that collapsed a lot of highways and was pretty bad. But the San Andreas Fault system is probably one of the most active in the United States. So many moderate to large earthquakes in Los Angeles have happened on this fault. Your mountain topography in coastal California is a result of the fault. And so those mountains that they have, kind of the California hills, is directly caused by the San Andreas Fault. Earthquakes since 1906 have cost hundreds of lives. Just hundreds? I would imagine it might be thousands, but maybe I'm wrong. And billions of dollars of damage. What's going to happen in the future of the fault? Los Angeles and San Francisco will just get closer and closer and closer until they're actually side by side in about 20 million years. Obviously, that's a long time away, and we've got lots of earthquakes between then and now. But that's exactly what's going to happen. So here's a picture of your plate. You see the San Andreas Fault running all the way up here. They've got some arrows to indicate which direction it's headed. So Los Angeles and the stuff closer to the ocean is heading northwest, and then your like landward side that's closer to the rest of the United States is actually headed southeast. And you can see that Los Angeles, which is right around here somewhere, and San Francisco, which is over here but on this side of the plate, are just slowly going to get closer and closer and closer to each other as the fault moves. And so we see in the movies, they're always like, Los Angeles is going to fall off into the ocean. It's actually not going to fall off into the ocean. It's going to slide upwards towards San Francisco, and they're just going to get like closer and closer together until they're the world's biggest city and they've won all the trophies. Let's see. So they talk about internal processes, and basically what they're talking about here is how the heat from inside the Earth helps drive plate tectonics and helps shape the overall structure of our planet. And so they're telling us that the Earth is layered. We have several different layers. We have the crust, we have the mantle, we have the different cores, and it's dynamic, which means it's constantly changing. There's things inside that are always moving, which is what helps drive plate tectonics. So they show us the three different layers again. We have the crust, which is on the very, very outside. We have the mantle, which is the thick layer in between the crust and the cores. And then we have the outer core and the inner core, which both kind of do the same thing, but the outer core is liquid, The inner core is solid because there's too much pressure. And so those are your four major layers of the Earth's makeup, I guess. So they talk about the inner core and outer core. Again, really similar here. Mostly iron and nickel. Iron and nickel are going to be a huge part of your cores. The inner core is solid because it has a super high pressure. The outer core is liquid, still very high temperature, but the pressure's a little bit less, so you can have it in the liquid phase. And we know this because of earthquakes. Then you have your mantle. Your mantle is very thick. One thing I will point out for plate tectonics, if I go back real quick, is your cores are going to be much more dense than your mantle. So the density of the cores are like a 10.7. And so they're going to be very dense. So they literally stay sunk down into the center of the earth because their density, they're heavier, and they're going to stay down towards the center. Where your mantle is quite a bit lighter, a density of 4.5. And then you get to your crust, and your density is about a 2.8 to a 2.5. And so literally each layer floats on top of the layer that's below it because it's much less dense. They have the lithosphere and the asthenosphere. The lithosphere is the crust. This is the hard rock that's on the outside. If you ever wonder how do the plates move around, so how does the United States literally just slide across the globe and end up somewhere else? It's the asthenosphere. The asthenosphere is like the slip and slide of the earth. When we see the continents moving around and undergoing plate tectonics, the asthenosphere is how they slide. It's like a semi-molten layer that allows the continents to kind of be moved on top of it. They call it a weak layer. So they talk about convection a little bit. The hot stuff from inside near the core of the earth rises up in these big plumes. Once it gets to the surface, it starts to cool down, and then it sinks. And those convection cells are what helps drive plate tectonics, which I'm sure we'll see in just a second. So now they move on to plate tectonics itself. What are the plates doing? How are they moving? What kind of interactions do we have? So they talk about the plates being broke up into pieces. They talk about the tectonics, which is the movement of the plates themselves. We see our large map, which has our different tectonic plates. And just remember, the plates match up to all the continents except for the Pacific plate. So we have North America, the North American plate, South American plate, African plate, as like, I don't know, geography. We split up Europe and Asia into two different continents, right? We call Europe its own continent, Asia its own continent. Geologically, they're on the same piece of rock. So we lump those together into one big Eurasian plate. We have the Australian plate, we have the Antarctic plate, and then we need one more because we've kind of put two into one here, and that's going to be the Pacific plate. The Pacific plate's the only major plate that doesn't have a continent on it. It's just pretty much all ocean. This is going to be an earthquake and volcano map, so you can see where our plates are at. If I can go back real quick. Where our plates are at, we're going to have all of the earthquakes and volcanoes, pretty much all of the earthquakes and volcanoes. So when I switch over to the next one, you can see that the earthquakes and volcanoes happen almost exclusively along our plate boundaries. There are some that kind of happen inside of those boundaries, but not a lot. The vast majority happen where our plates are interacting. So we talk about seafloor spreading. This is where two plates are splitting apart. You have a divergent plate boundary. And basically, just imagine I have the Earth, and it's being cracked open like an egg, and I'm pulling these two pieces apart. What's got to happen? Lava or magma is going to come up from inside the Earth, and it's going to fill that crack. And so when it fills that crack, it's going to cool down. And what's going to happen is I'm going to have more plate being created. This is how we create new lithospheric plate. And so this is the seafloor spreading where your oceans are essentially created. Not the oceans themselves, but the land that the oceans are on in a way. So sinking plate generates volcanoes and earthquakes. And I kind of have this out. We were going over this in Earth and Space the other day. If I have at the surface some continental plate and some oceanic plate, if the oceanic plate gets pushed downward, this part that gets pushed underneath the surface is going to melt. Anything that gets pushed down deep into the Earth's crust is going to start to melt. And so what they're telling us here is any plate that gets pushed down and starts to sink is also going to melt and create volcanoes. That's what happens anywhere you have plate being pushed down. And so they kind of show us that in this picture. You have your oceanic plate, and it's going to get pushed down underneath your continental plate. As it gets pushed down, it starts to melt. This melt is going to bubble back up, and it's going to create volcanoes that happen right near the shoreline. And so think of the volcanoes that we have in Washington State. These are going to be the volcanoes that you have there. As the Pacific plate gets pushed underneath California and Washington, it kind of bubbles up and feeds those volcanoes so they have a chance to stay active. Same thing happening here. You have your oceanic plate being pushed underneath. They're showing you earthquakes that are happening. So you can see your shallow earthquakes are not that strong. The deeper your earthquakes go, the stronger they're going to get. And then you have your melting coming up and feeding your volcanoes right there. Let's see. Plate tectonics is a unifying theory. So they're talking about plate tectonics and how it solves a lot of problems that we've seen. So they have the bullet points here for all the different things that plate tectonics kind of fixes for us. So how the Earth works, evolutionary change, because we see different animals evolve in different ways. Knowing that they were isolated on a certain continent or a certain island helps out with that. How the plates are moving, we can actually see that now with GPS. So we see that the plates are moving, and this helps explain it. The distribution of where our earthquakes happen, where our volcanoes happen, similarities among fossils that we see, and changes in the Earth's magnetism. And so someone from Texas, well, we talked about yesterday how we get a lot of tornadoes, but we don't get any earthquakes, and we don't have any volcanoes. So someone from Texas might be like, yeah, why don't we have any earthquakes or volcanoes? It's just like it's never happened here. It's never going to happen here. Why is that? And that's because we're not near a plate boundary. We're like smack dab in the middle of a giant plate. And the earthquakes and volcanoes really only happen at the edges. And so that's kind of important for us. And then they say down here at the bottom that convection, like I talked about earlier, hot stuff rising, cold stuff sinking, is probably what drives plate tectonics and actually makes the plates move. So you can see here in this picture, your cores are going to be super hot. They're going to heat up this material in the mantle, which hot things rise, which we learned that in science. Hot things rise. That's your convection cycle. And so as it rises up, something else has to sink down to take its place. And in between that rising and that sinking, I've got to have an area that goes side to side. So those side-to-side areas are what's going to pull the plates in a certain direction and help influence the movement of the plates in plate tectonics. And so we believe this is a major contributing factor to why the plates move the way they want to, and why sometimes they just change direction, which we never really had a great explanation for, because they'll be going one way. Sometimes they'll just stop and go the opposite direction or a different way. And that makes sense if you say, oh, well, the convection cycle changed. It moved a little bit, it reoriented itself, and now it's dragging the plate in a different direction. We're a little bit more comfortable with that. So what? Now they go through the types of plate boundaries, which we're not going to go through in this chart. There should be some pictures like there are right here. So different plate boundaries. You have oceanic continental. When your oceanic plate runs into a continental plate, the continent is always going to win. The continent is going to float. The oceanic plate is going to sink. The oceanic plate is going to get melted as it gets pushed underneath, and so it's literally going to get destroyed. Your continental plate is going to win the chicken battle in the pool and stay above water and survive to see another day. And so that's why the continents are all very, very old, like billions of years old. I think on every continent we found a rock that's at least 3 billion years old, while the oceans are very young. we don't have any oceanic rocks that are over like 200 million years old. So all relatively very young. When you have oceanic run into oceanic, it's just a coin flip as to which one stays up and which one goes down. One of them is going to get pushed underneath, though, and when it does, you're going to have melting, and you might have some volcanoes that come out of that. And then continental, neither one wants to go down at all. They both want to stay up, and so when they smash into each other, it's going to be like a car wreck. Their hoods are going to get all crumpled up, and you're going to get a mountain range right in between where the two continental plates smashed into each other. But when you have continental, you don't really get any subduction. You don't get a continent being pulled down underneath another continent. So those are your three different types of plate boundaries. Oceanic, continental, oceanic, continental. How fast do plates move? Just remember they grow about as fast as your fingernails do. So in a year, maybe just a couple centimeters of growth. Not that much. Same thing with the plates. They move about a few centimeters per year. The slow ones are maybe 2 or 3 centimeters per year. The fast ones are like 12, 15 centimeters per year, but still not super duper fast. So what are they showing us here? Oh, this is a map that shows the direction the plates are moving and how fast they're moving. So you can see San Andreas Fault. It's actually moving pretty fast. It's going side by side here at a rate of 35 centimeters per year, which is pretty fast. No, sorry. That's millimeters per year. So that's a little bit slower. That's like 3.5 centimeters per year. So not too bad. That's pretty normal. The Juan de Fuca plate is spreading here. That's happening a little bit faster, like 5.3 centimeters per year. If you come down here, south of Mexico, and you look at like the Nazca plate where it's spreading right here, that's like 12 centimeters per year. So that's pretty fast. That's creating a lot of plate. So you can see they all have their different speeds. They don't necessarily match up to anything else, and they're all pretty unique, which makes studying it kind of interesting. Mid-Ocean Ridge is discovered by Harry Hess. I talked about Harry Hess last semester, the military guy who in World War II is traveling from the United States over to Europe to fight in the war, and in his travels across from the United States to Europe, back and forth, discovers that there's this giant mountain range in the middle of the ocean. And it's like, hey, what's up with that? Why is there a giant mountain range in the middle of the ocean? And as they just did more and more exploration and tried to map it and figure out some things about it, it kind of fits in really well with plate tectonics. It explains a lot of things. One of the other things they discovered while they were looking at that mid-ocean ridge is that we can record, or we can see that the magnetic field has been recorded in the rocks, and that it flips back and forth. And I'm hoping for a picture here in a second. There it is. Let me actually go back 2 slides. So what happens, we have the Earth's magnetic field just like this. The North Pole is north, the South Pole is south, which doesn't really make a lot of sense because a magnet isn't really north and south. It's positive and negative. And so right now, what we think is the magnetic North Pole is positive, I believe. Is that right? Does that say that here? It doesn't. But anyways, yes, so the North Pole is positive. So when we get our magnets on our compasses and the little needles magnetized, it's going to point towards the North Pole. We're pretty close to it. But there are times when the magnetic poles flip. And essentially, if that happened today, tomorrow, you would take a compass and it's going to point towards the South Pole. It's going to lead you in the exact opposite direction. And so we've never actually been around while one of these has happened. So when we started to see the rocks, everybody was like, why is it like this? What's going on here? And it actually took us a little while to kind of figure out that the poles flipped like they do. And so one of the ways that we discovered this was we saw these magnetic stripes in the ocean floor. And so as Harry Hess is going back and forth from the United States to Europe and taking these readings of this mountain range that he finds in between the United States and Europe, his magnetic readings are getting these like stripes. So you get like a stripe of black, a stripe of white, a stripe of black, and it just goes back and forth with these black and white stripes, showing that the magnetic poles for the rocks are reversed. They're pointing in the opposite direction. And so it took them some time to figure out that every so often those magnetic poles flip. And once we knew that, that helps us understand more about the rocks and how plate tectonics works. So they're going over here how we figured out that the seafloor, your oceanic crust is no more than 200 million years old. The oceanic rocks are very, very young. Your continental rocks are very, very old, which helps explain why we're seeing the way the plates move around, as opposed to like every plate for itself, everything being destroyed. This is kind of showing you how your poles reverse. So your magma comes up, you have magnetic minerals in the lava, and they kind of line themselves to the poles. And when the lava cools down, they get trapped in place and they can't turn anymore. So you can see that kind of recorded in the rock. What is this? This is the map of ages of the ocean floor. You can see the continents are not colored in, just the oceans are. And you can see that the oldest ocean rocks are like 200 million years old, which is not very old at all. It's very, very young. Each of the continents, you're talking like billions of years, where the oceans, you're not even like a quarter of a billion years. Very, very young for the oceans compared to the continents. They talk about hotspots like Hawaii. Here's the Hawaiian island chain. And if you didn't see it last semester, you can see that the Hawaiian Islands, they don't come above the ocean surface, but the Hawaiian Islands actually stretch underwater all the way up towards Japan and Russia. And so this is a very, very long island chain. It's just most of the islands are underwater and never really got above water. But yeah, we also have a new Hawaiian island coming soon to an ocean near you. Pangaea and the present continent. So they talk about Pangaea and the breakup of Pangaea about 200 million years ago. So this was the last time we had a supercontinent and all the continents were together. And then at some point in time, about 180 million years ago, 200 million years ago, they start to break apart and go their separate ways to their current locations where we know them today. But just imagine if you lived here, yeah, all the continents are together. What's on the other side of the globe? Like the world's biggest ocean. And so that would be really strange weather and a really strange planet to live on, where all the continents are just together and you have one giant, like almost never-ending ocean. Let's see. Oh, evidence for plate tectonics. You can see that fossils don't really make sense unless you have a supercontinent like Pangaea. We've got lots of different animals. Like, no offense, look at this guy. He's not going to win a marathon. We feel each other here. He's not going to walk all the way from Australia. Well, no, he's not on Australia. What's he on over here? Antarctica. He's not going to walk all the way from Antarctica to India and to Africa. This guy's not making that swim across those oceans. And so how did this guy get on all these different continents with fossils kind of everywhere? Well, it makes a lot more sense if the continents were together. Same thing with this dinosaur. Not a strong swimmer, not going to be able to swim across the ocean from South America to Africa. And so how do we find those fossils in the same place at the same time? Because the continents were together, and he literally just walked there. Same thing with glaciers. India shouldn't have any glaciers at all. The vast majority of Africa shouldn't have any glaciers at all. But we see glacial evidence all along here in areas that couldn't support glaciers at all today, no matter how bad the weather got. So how do we explain the glaciers? Well, you move all the continents. You put them together. It's actually closer to the North Pole than the South Pole, and you see a lot of glaciation happening there. And so that makes sense. Now we're okay with that. We can understand glaciers in Africa and glaciers in India and in Australia, where we know there are no glaciers, just giant spiders. So how do plate tectonics work? Like I said, we think the main driver of plate tectonics is going to be your convection cycles. So heat going up, cold stuff coming down. They also have the ridge push and the slab pull. And basically how that is if something's getting pushed down, gravity is just going to pull on it even more. So once it starts to get pushed down even just a little bit, gravity takes over and tries to pull it the rest of the way. That's kind of what's going on there with ridge push and slab pull. Here's their example. You can see this plate is already starting to go down. Gravity is going to pull it down even more, and it's going to pull on the entire thing. And at my mid-ocean ridge, where my mountain range is created underneath the ocean, this is also kind of going downhill. And so gravity pulling on this part of the plate right here is going to kind of push it along. And so those are two different sides of the same coin, slab pull and ridge push. And then I think that's it. Yes, chapter 2 summary. We got through that very quickly. That was not bad at all. So tomorrow I will have some assignments open, and we will kind of work through those. A couple of them I'll probably leave for y'all to do on your own, but we might work through a couple of them like together as a class and just kind of talk about them since they're kind of new and fantastical. All right. Wonderful class, everybody. I will post this online for my remote students and try to get some more stuff done. Try to not fall asleep.